Okay, hi. My name is Antony Polukhin. I'm one of the Boost C++ libraries developer, and I work for Yandex Taxi. Today, we're gonna talk about a lot of metaprogramming stuff. We'll talk about how to implement reflections in C++ 14 without any macro, markup, nor external tooling. And before you start scaring, all the stuff we're going to talk today are already implemented in the Boost PFR library. It's not part of the Boost, hopefully yet. Someday it will become, I hope so. All the things are in there. You can find that library at the link. It's on the GitHub, Polukhin magic get. So now, let's start. Imagine that you have some structure. It has some name. It has some fields. Those fields have also some names. Now, with that structure, we can write the following code. We can include IOStream header. We can include Boost PFR library. We can define our structure. And after that, we can write a main function. In that main function, we create a variable of our structure type, and aggregate initialize it. After that, we try to output that variable into the std.cout. And at that point, a compile time error should happen. Well, we have not defined nor declared the austream operator here, so the compiler will fail to find it. However, the code works. And what's more interesting, it outputs the content of the structure. And it outputs the content exactly. It knows that the third field is a double, and it outputs it as a double. We can go back to the example, change the name of the structure, change field counts, change names of the fields. The example will continue to work. So, how is that possible? Where is that austream operator? Well, we definitely don't have the right one in IOStream header, and we don't have one in this source file. So it's somewhere in the Boost PFR library. And here it is. The interesting thing here is that it accepts any type, any user-provided type. So it works with any user-provided types. There is an enable if at the top, and it means that this operator works only if user have not already provided the austream operator for that type. If there is a type, if there is an austream operator for that type, the user one will be chosen. Otherwise, this austream operator is used. And in the body of that austream operator, there is a Boost PFR write function call. That function is pretty trivial. It outputs some curly brackets. And in the middle, it calls the print function. There are some template arguments there. And what's more interesting, there is a Boost PFR tuple size _v template variable. Looks familiar, yeah? We have something close for stud tuple. But in this case, we're not working with stud tuple. In this case, T is a user-provided structure. So this function returns fields count in the user-provided structure, in any aggregate initializable user-provided structure. That's interesting. Let's go further. Print function. Outputs or not outputs some comma, and gets a reference to a field by an index. User gave us some structure. It has some fields. Now we can access a field by index, just like std.get does with tuples. After that, we call print again for the next field. That was the introduction. For the next 40 minutes, we'll try to implement tuple size _v template variable, and we'll try to implement the get function that works with any user-provided type. Let's start. So, how to count fields in some user-provided structure? We've got user-provided structure T. That's the name of the structure. And that structure is a plain old data type. So in other words, we can write the following expression for that structure. We can try to aggregate initialize that structure with some amount of arguments. That expression will compile if the arguments count is less than or equal to the fields count, and if each type of the argument matches the field type in the user-provided structure T. Now, from that, we can get the fields count. Here's how. We try to aggregate initialize user-provided structure T with some huge amount of arguments. That will fail to compile. We drop off one of the arguments and try again. This will also fail to compile. But at some point, the arguments count will be equal to the fields count, and that's it. We know the fields count. How many arguments do we need to start with? Well, if user-provided structure contains only chars, bytes, unsigned chars, signed chars, or some other data types that have the size of 1, well, in that case, size of the structure will be equal to the fields count in that structure. If user-provided structure has some other data types in them, like integers, doubles, std strings, then the fields count in that structure will be less than the size of the structure. If user has bit fields, well, we have to multiply size of the structure by char bit. And that will be the maximum amount of arguments we need to try to aggregate initialize user-provided structure. We've got a problem here. We don't know the type of each field. So even if we guess the arguments count, the fields count, the expression will fail to compile. We need somehow to deal with that problem. And the solution is quite simple. We create a structure, it's named ubic, and in that structure we've got an implicit templated conversion operator. So instances of that structure could be implicitly converted to any data type. You can convert an instance of that structure to an integer, to double, to std string, to std vector of std strings, to anything. Now we've got the whole recipe. User give us some data type, some users provided structure T. We try to aggregate, initialize that user provided structure T with arguments count equal to the size of that structure multiplied by char bits, and each argument is an instance of ubic. That will fail to compile. We drop off one of the arguments and try again. It will fail to compile. Drop off one of the arguments, compiles. Great. We've got the fields count. Now, how would it look in code? We slightly modify our structure ubic to be more usable in template expansion packs. We just added an ignore variable here. After that, the whole implementation is just two functions. We got two functions, detect fields count. Well, both of them have the name detect fields count. First function is slightly more specialized than the second, so the compiler will try to use it first. And look here. We've got an aggregate initialization in the return type of that function. So if that expression succeeds, if the compiler could compile that expression, great. We go into the body of the function, and from there, we put fields count into the output variable out. Otherwise, if the expression failed to compile, the compiler will think, this is a substitution failure. It's not an error. I just need to use a less specialized function. And the compiler will use the second function. Second function calls detect fields count again, but drops off one of the arguments. It calls detect fields count with less arguments. And it works. But there are some problems here. Who can guess those?
Nested structs, maybe?
Nested structs, yes. What else?
Let's go to what? 256, then you have a recursion in there. So
Yeah, the problem is template instantiation depth. So compilers have some limitations. If you go too deep, if you have too many fields in your structure, you're screwed.
but you can linearize it.
Yes, don't spoil. So this naive approach works, it compiles, but takes a lot of time. We have to make it faster. We have to make it better. Let's take care of simple cases. Cases where we're working with aggregates, and each field in that aggregate is default constructible. For such aggregates, we can write aggregate initialization without any arguments. We can write aggregate initialization with 1 ubic, 2 ubics, 3 ubics, many ubics. Some of those expressions will fail to compile, others will succeed. Now let's put all the failures and successes into an array. Now, the question. Does it look like a partitioned array? Come on. Come on. Yes, 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 it's a partitioned array. So we've got a partition point. At that point, pluses, our successes, transferred into failures. After some point, we can add more instances of ubic, and that will fail to compile. So, and what's the fastest way to find a partition point? Binary search, yes. However, we've got a problem. Stud lower bound doesn't work in this case. We need some kind of a binary search that does enable if trick and works at compile time. But yes, it's a binary search. Here's how we can implement it. We got that array of all possible failures and successes. It just have the size of the structure multiplied by char bits. We jump in the middle of that array and try to aggregate initialize user-provided structure T with this amount of arguments. If that succeeded, great, we drop off the left part of the array. Repeat the procedure, jump in the middle of the remaining part, try to aggregate initialize that stuff. If that fails, drop the right part of the array. At some point, we'll keep repeating that procedure, and we've done. We've found a partition point. And what's more nice, we've done logarithm instantiations, and we have logarithm instantiation depth. So it's really hard to exceed the compiler limit for instantiation depth. Even with huge structures, it's hard to have structures with fields more than 2 in power 256. That was a simple case. We've got other aggregates. They're creepy. Well, it's C++. So there may be aggregates that do not have default constructors or some deleted constructors. In that case, our array of failures and successes, not nice. It's not partitioned. We cannot do a fast binary search here, but we can deal with the problem of template instantiation depth. If we use the naive approach and we'll be dropping one argument by one, it will be a linear instantiation depth. So we'll fail our compilation really fast because we'll exceed the compiler instantiation depth limit. What can we do? We can write a bad version of binary search. Instead of dropping off one of the parts of the range, it just continues binary searching in that remaining range. So here's how it looks like. We got that array. We divide it on 2 parts. And now in each of the parts, we repeat the procedure. We'll keep dividing that array again and again and again. And at some point, we've got really small ranges. There's only one integer in them. Now, we have to try the aggregate initialization for each small range. And now we've got that array of failures and successes. We still got linear instantiations. Not nice. But we've got logarithm instantiation depth. And that's nice. That means that we can use this approach, and we won't hit the compiler limit. Now, how to get the field type? OK, no one saw my old presentation a few years ago. Great. So here's the idea. We've got that aggregate initialization of user-provided structure T with some instances of UBIC. During that aggregate initialization, an implicit conversion operator is called for the UBIC. And inside that implicit conversion operator, we know the type. It's the type of the field. Great. Now we have to grab that type and put it to some outer scope where we can use it for the better good. We need some kind of a variable where we can put a type and then in outer scope reuse that type, extract that type from a variable. Unfortunately, there's no such way in C++. You cannot just get a type, assign it to a variable, and use that variable in the outer scope at compile time. So it doesn't work really well. But if we're working with plain old data types, those are quite simple. Plain old data type is a type that contains only fundamental types, or another plain old data type that also contains only fundamental types. That means that, well, we don't have many fundamental types. We can assign an identifier to each fundamental type, and we'll get some kind of a map. It maps a type to an integer, to an identifier. And we can, after that, map a type to an identifier, put that identifier into some integral field, to some output variable, and reuse that result in outer scope. Extract type from integer, convert an integer back to type. Here's how to do it. We again modify our structure UBIC. This time, it has an output, a pointer to some output array. And we change the implicit conversion operator. Now the implicit conversion operator outputs in the array type of the field we've met. There is a function that's called type to ID. What does it do? Yes, converts type to ID. So we need to register all the fundamental types. We just write some macro. We'll use it only internally in the library. User doesn't know about that. That macro creates two functions. First function, type to ID, converts type to identifier. Second function converts identifier back to type. And now we register all the fundamental types. All of them didn't fit on the slide because there are plenty. There are about 30, 32. So some of them are on the slide. After that, we can get the type of each field. Here we've got a function, type to array of type IDs. Inside that function, we create a temporary variable and aggregate initialize that temporary variable with some instances of UBIC. During that aggregate initialization, an implicit conversion operator inside the UBIC will be called, and that implicit conversion operator will output the type of the field in the output array of types. Now, final step. At line 0, we have that array of types. It's identifiers. It's a stud array from integers. At line number 1, we convert an integer to integral constant. At line 2, we convert integral constant back to type. And at line 3, we create a stud tuple of types, and each type matches the field type in the user-provided structure. Great. Final step. We have to implement the get function. User gives us some integer. It's index of the field he's interested in, just like with stud get. User gives us a runtime variable v. And here we've got a tuple. It's a stud tuple of types, and those types match types of the field in the user-provided structure. Now, how to convert that user-provided structure to some kind of tuple. First solution, the ugly one. We've got a reinterpret cast here, and we're reinterpret casting two unrelated types. We reinterpret casting user-provided type to some tuple that has the same layout as the user-provided type. Well, it's not a nice solution because that's an undefined behavior. There are some platform-specific workarounds to make this stuff work. They kind of work, but it's still not really nice. There is a better way to do that. We still have reinterpret casts, but this time it's safe and they don't bring us undefined behavior. So what can we do here? We got a variable, user gave us that variable, and here we get the pointer to the first byte in that user-provided structure. That pointer is a pointer to the first field in the user-provided structure. If we need some other field, we can count the offset of that field. We've got a tuple with the same layout. We can count the offset. And we can get now a pointer to a field we're interested in. After that, we can reinterpret cast unsigned char star to a type of that field and return a reference. That's it. Works. Whew. However, there are problems. User can write his own enums, and those enums we can't predict them all. We cannot register those enums in our map of fundamental types, in our map of identifiers and types. There are too many combinations. User can create its own enum with crazy names, so we cannot just take it and register in that map. And we cannot register that information in the map, well, because stateful metaprogramming in C++ is not really permitted. But we can represent enum as an underlying type. The underlying type is a fundamental type, so we can use it here. Other problem, nested structures, as someone told from the crowd. Same problem. User can invent its own structures. We cannot just register all the possible structures in our map of types and identifiers. We don't know that knowledge. User may create its own structure somewhere after including our header. We cannot take it and register. But instead of that, we can do the reflection recursively. In Boost PFR library, it's called flat reflection. And here's how it works. We've got structure 1 and structure 0. User asks us to reflect the structure 0, and user asks us to reflect structure with number 1. And that structure has a structure 0 as one of the fields. We can do that, but we can go recursively and reflect the content of structure 0 as if the whole content was in structure 1. So in other words, we're kind of reflecting this structure. It's called a flat reflection. It's the best we can get with this approach, but it works. Other pitfalls. If we want to reflect const pointer, volatile pointers, pointers to const volatile pointers to volatile pointers, and other stuff, we have to do a lot of computations, and it slows down your compiler, your compilation. And final drawback. This stuff works only with plain old data types. A few years ago, I've been giving some close talk about how to implement reflections in C++ 14. And that was almost the last slide in that talk. So after that, I've asked, does anyone have questions? People started asking questions. I've answered those questions. Lisa Lippincott said that he found a bug in my implementation, which was kind of surprising. She found a bug just by looking at the slides. That's just genius. Well, I fixed that one. After that, I traveled back home to Russia, started working, and at some point, I've got a mail. And the person was saying, "We can do better." And he gave me a recipe, and that was, well, it was hard to acknowledge that, yes, it works. But yes, it works. I've implemented that in the Boost PFR library, and after half a year, another person appeared and said, "We can do much better." That was shocking, but that works also well. I don't really understand how, but it works. So now, let's take a look at those solutions. Better field type detection. A slightly creepy one. Yes, the type detection before that was not so creepy. Now, we've got our aggregate initialization of user-provided structure T, and inside that the aggregate initialization and implicit conversion operator for UBIC is called, and inside that operator, we know the type. But instead of taking that type and pulling it somehow into the outer scope, we can go deeper. We can repeat the procedure and remember the type. So we proceed recursively, and at some point, we get all the fields type just in tuple. Here's how to do it. We create a function for each field in depth. First template parameter is a user-provided structure. Second parameter is an index field we are interested in. And after that, there is a pack of types of fields we already met. After that, there are some runtime parameters, for example, reference to the user-provided structure and some callback. Inside that function, we call UBIC constructor next and give it a type and then the index we're interested in. Inside that UBIC constructor next, there is an implicit conversion operator, no surprise here. And inside that implicit conversion operator, we call for each field in depth again. This time, we call it for the next field. And we remember the type we've just met. Repeat the procedure multiple times, and we reflected all the fields. Great, we have to call the callback and convert a reference to user-provided structure to a tuple of references. And each reference in the tuple is a reference to the field in the user-provided structure. And it works in C++14. And it works not only with plain old data types. It works with any aggregate initializable type, which is awesome. But it has big compile time overheads. We do that aggregate initialization many, many times. And we relying on compiler cleverness for eliminating unnecessary copies. Well, actually, we don't really trust compilers, so we do a bunch of static asserts that the compiler could eliminate all the temporaries, all the copies. That kind of limits our where we can use that, because sometimes the checks are really strict, and we just better be strict than get some runtime overhead. And finally, yes, that not always works because of those strict checks. We can do better. This is an insanely creepy solution. And it's the most brilliant one I saw. So, the essence. We've got our map of types and identifiers. And we need some way to expand that map. We need some way to add new elements in that map during our instantiation or during our implicit conversion operator's call. But unfortunately, Stateful metaprogramming is not allowed by the C++ standard. And people who do the C++ standard, they're really serious about that. Core working group in the C++, they take a look at that. They keep a hand on the pulse and always check that there is no stateful metaprogramming allowed. They even feel issues that in some cases the state leaks out of the constexpr context. We can use it. So, we've got a structure tag. And inside that structure, we've got a friend function named loophole. That tag, it accepts two template parameters. First template parameter is a user-provided structure. Second template parameter is a field we're interested in. This just forward declares some loophole function without a result type. Now, also we have a function definition structure. And inside that function definition structure, we define that loophole function. We've got its body, and we've got a return type for it. So now this auto somehow remembered that that type. So declare, define, now the loophole from our structure with this index returns us the type of the field. How to implement? How to use it? OK, we still have the implicit conversion operator in our structure ubic. And it has a really creepy enable if statement. In that enable if statement, we call this function ints, and it forward declares the loophole function. After that, we call function definition, and inside that function, we remember the type of the field. We provide the type of the field right here. Does it work? Yes. We've got a structure test. It has some fields. We say aggregate initialize that structure test with loophole. We say that, yes, we're interested in structure test. And we're aggregate initializing the field with index 0. After that, we can static assert that loophole from test with index 0, the return type of that function is char. And that assertion works and passes. Great. What are the drawbacks of this approach? Come on. What do people do with bugs? Yes, they fix them. So someday, the core working group will fix that issue that we're exploiting. And in that case, this recipe will stop working. But the previous two will continue working. But finally, there is one recipe that always works, but it requires C++ 17, not C++ 14. And this one is really simple. And I've invented it. Yes. So, function s-tuple impl. User give us some runtime variable. For that runtime variable, we detect fields count, just like in first slides. Now, we've got the fields count, and that's a compile time known constant. With that constant, we can write if constexpr. Andrei was talking a few hours ago that with if constexpr we can do only boring things. Well, kind of. So, in that if constexpr, we've got a structured binding. So, if there is one field in the user-provided structure, we decompose it into one field. And after that, we create a tuple with references to the field. So, we've got a tuple with one element, and that one element is a reference to the field inside the val argument. If we got two fields, we decompose them to two elements and create a tuple of references to those fields. We can write a lot of these if const expr. I didn't. I've made a generator for those. So there is a huge function with count 300 and more, and it works. And it requires C++17. And yes, the question, do we need all this? Where can we use this stuff? Is it useful? Well, it's useful. Some companies are already using it in their production code. And the Boost PFR library has a bunch of features out of the box. For example, it has comparisons out of the box. You've got your structure. You have to do nothing. You just can compare two structures with each other. You can compare on equality, less than, greater than. Just works. Also, there are heterogeneous comparators. So if you've got a structure with name A and structure with name B, and they have fields with the same type, you just can compare them, and that's it. Also, IOStream operators. You get a structure, you want to save that structure into the file, you just write std fstream and save that structure to the file. You want to read that function structure from a file, great, std fstream, and read that structure from a file. Serialization to a file never was so simple. What's more interesting? We've got hashing functions here. You don't have to write your own hash functions and don't have to deal with all the hash combine stuff that is not in the standard. You just use a ready hash function, and that's it. And finally, we'll get all the functions that are useful in functional programming. Or we get the same functions for structures as you have for tuples. You can get arbitrary field from a user-provided structure. If you try to give an index greater than the fields count in the structure, you'll get the static assert. You can initialize your structure from std tuple. You can initialize std tuple from a structure. You can initialize structure from a structure, but they have different types. You can write your own serializers and other stuff. That's all we have out of the box in the Boost PFR library. Well, a little bit more than that, but that's the generic idea. But also, you can write your own stuff. You can write some user-defined serializers. For example, some people told me that they were working on some radio-like company, and they've got a huge amount of aggregate initializable structures, and they've got different types of wires. So for each type of wire, they need a separate serializer. So they've got 3,000 structures, 9 types of wires, and they've got 27,000 serializers and almost the same amount of deserializers. With that library, they need only 9 serializers and 9 deserializers just for the concrete type of the wire. Also, you can do basic reflections, static assert that user-provided structure has this type of the field. You can create your own type traits. For example, is continuous layout or has unique object representation. This is available in C++17, but well, you can do it in C++14 now. If you're writing some intrusive containers, you can use this library to find bits in a user-provided structure that are not used and reuse them. You write an intrusive container that implements some kind of std set, that is a binary tree. You can find unused bits in user-provided structure and store red or black flag in that bit. Also, if you're a Boost developer, you may wish to use this library for many funny stuff. Like example, imagine that you're inventor of the Boost Spirit. Now, you can update your library, and write the boost spirit in a way that it will work with any user-provided structure without boost fusion strange macro thing. You write a date-time parser and just give it a structure that represents date, time. That's it. It will parse directly into a structure. Now, final slides. Acknowledgements. There are people who helped me with this library, who gave them some ideas, reported bug fixes, so I'd like to say thank to them right now. First of all, I'd like to say thank you to Alexander, who invented the loophole trick. I'd like to say to Bruno for the recursive reflection trick. I'd like to say thank you to Chris Beck for removing undefined behaviors from reinterpret casts, and he even made a pull request that was accepted. He's done everything right, and it works. It's great. I'd like to say thank you for a butcher. It's a nick from GitHub. He added a lot of functions in a stud tuple manner that does tying from user-provided structures and something like that. I'd like to say thank you to Lisa Lippincott and Alexei. They found the same issue in my early version of the library at the same time in different countries without talking with each other. That's cool. And I'd like to say thank you to all the other people who were using this library, testing it, and reporting some issues that are hopefully now all fixed. That's it. Thank you for listening. You can contact me by email. You can find me on GitHub. There's also a link to the page that leads to another page when you can find all the C++ proposals that I'm proposing in the C++20 and further. And if you know Russian, you can go to this site. We discuss there are different ideas for improving the C++ language. Some of those ideas, we take it, improve, and with the author proposed for inclusion in the C++ standard. If you need something to read about Boost, then there are some books about the Boost. They even have a Korean version. If you know Russian and want to read non-technical literature, then there are perfect rhymes from this author, Anonymous. There is love, there is romance, and a little bit of cannibalism in there. Everyone likes it. So now that's it. Now it's time for questions. Please use the microphone.
I was just wondering if you're thinking about using features that some compilers are starting to support that does introspection instead of instantiating tons of templates when it's possible. Like I know libclang has some support for some of these things.
That's interesting. I need to take a look at those. I'll find you and ask about those features.
Yeah, so the loophole trick that you talked about, what compilers and in which versions do support this trick? And what's the time frame where we can still use it? Because we actually would have another application for this trick.
OK, it works on Microsoft Visual Studio, it works on GCC, it works on Clang, and I have no access to other compilers, but probably it works there. Well, it works on Visual Studio. What else you need?
I'm surprised.
About the time frame. So, since C++ 17, we've got another trick to do the reflection, this one. If the issue will be fixed, well, I hope that it will be fixed for C++ 17 and more modern versions of the C++. Otherwise, well, it's a nice argument for moving to C++ 17 rather than using C++ 14. but I have no idea about when they're planning to fix that issue, and I'm quite sure that it's not high in their priority list.
Okay. Thank you.
All right, thank you for coming and listening.